So we are given a positive integer n, and we should return the number of binary strings of length exactly n. As you might know, this is a classic mathematical problem, and its answer is given by the formula 2 at power n. And let's see why is that. Let's imagine all the n positions of our binary string. The first character could be either a 0 or a 1. So there are two options of picking the first character. Then, the second character could be a 0 or a 1. So we also have two options of picking the second character. So if there are two options of picking the first one and two options of picking the second one, this means there are a total of 2 cross 2 options of picking the first two characters. Following the same line of reasoning, there are 2 at power 3 different options of picking the first 3 characters, and so on and so forth, resulting in a total of 2 at power n options of picking each of the n characters. So this is where the formula came from. Now, we will see how to achieve the exact same result using dynamic programming. For that, we will analyze something that we call the evolution of solutions. We will start with the most primitive ones, which are the binary strings of length 1. There are exactly 2 of them, and they are 0 and 1. Now, one step further in evolution, let's think about the binary strings of length 2. They consist of 2 characters, which we will note as 0 and as 1. So how did these strings evolve from the previous ones? They have an extra character at the end. This character could be either be a 0 or a 1. And the other character, which is S0, is part of the previous set. In conclusion, in order to obtain the binary strings of length 2, all we have to do is pick each binary string of length 1 and push either a 0 or a 1 to the end of it. And here there are all the binary strings of length 2. They are a total of 4. One step further in evolution, let's think about the binary strings of length 3. They consist of 3 characters, which we will note by S0, S1, and S2. How did they evolve from the previous ones? Well, they have an extra character at the end. This character could be either a 0 or a 1, and the prefix of length 2, which is S0, S1, is part of the previous set. So all we need to do is pick each binary string of length 2 and push either a 0 or a 1 to the end of it. And here there are all the binary strings of length 3, and as expected, they are a total of 8. We can already notice a relation between each set of binary strings and the previous one. So let's use this relation according to what the problem asks for, which is the number of binary strings of length n. This n is very important as it is the only factor that influences the answer of the problem. For different values of n, the problem has different answers. So let's define what the problem asks for according to n. dp of n is going to be the number of binary strings of length n. Back in the evolution of solutions, we can say that dp of 1, which is the number of binary strings of length 1, is equal to the size of the first set, which is 2. Remember, the strings in the second set consist of 2 characters, which we will note by S0 and S1, where the second character could either be a 0 or a 1, and the first character is part of the previous set. So we created these little sets by pushing 0 or 1 to the end of each binary string of length 1. As you can see, each of these sets has a size equal to dp of 1, and that is because each string from the set corresponds to a binary string of length 1. And here is the relation. dp of 2 is obtained by doubling dp of 1. Following the same line of reasoning, the binary strings of length 3 consist of a prefix of length 2, which is part of the previous set, and either a 0 or a 1 at the end. Again, two sets are going to be formed, both of them of size dp of 2, and the relation is confirmed. dp of 3 is also obtained by doubling the previous value, which is dp of 2. You can imagine each value of dp as a node in a graph. We call these values states, and as you have seen, they are defined by those numbers that the answer of the problem depends on. In our case, only n. We call the most primitive solutions the initial state or the base case. The answer of the initial state should always be initialized because the other states depend on this one. The relation between states is called the transition function or the recurrence relation. In our case, this relation takes place only between consecutive states and tells us that the answer of some state is defined by the answer of the previous state multiplied by 2, except of course of the initial state. We call the answer of the problem the final state. That is the value that we should have computed in the end. So, for this problem, what we should do is first perform the initialization, which is dp of 1 equals 2. Then, perform the computation, which is for each I between 2 and n, dp of I equals dp of I minus 1 crossed 2, and in the end, return the answer, which is dp of n, and should be correctly computed. Both the time and memory complexities of this approach are big O of n. So, you probably ask yourself, okay, but why would I ever use a dynamic programming if I can solve the problem just by coming up with a formula? And that is a very good question. You should never solve a problem using dynamic programming if that problem can be solved only by coming up with a formula for the answer. But you should know that the set of problems that can be solved with formula is included in the set of problems that can be solved with dp. In other words, every problem that can be solved using a formula can also be solved by using dynamic programming, but not vice versa. dp should be used when to a problem are added some constraints or some rules which make it very hard or even impossible to solve it just by coming up with a formula. For example, to this problem, I could have added 2 more constraints. You are given 3 integers n, k, and d, and you should count the number of binary strings of length n with at most k consecutive ones, and the distance between each 2 ones is less than or equal to d. As you can see, 2 more constraints have been added, and coming up with a formula is not so easy. We will solve this problem along with other problems similar to this one in the following lessons.